What's this thing here? I brought this thing in just because I saw it in the back. It's an image I have in my head whenever I'm talking about silicon. Now, this is not an image of a silicon crystal. It's actually an image of something, it's a model of something, I think it's called a xenolite, a thing that's used for filtering. It's a little bit more complicated. But when someone like me thinks of silicon, I think of a very regular structure like this. Now here, what are these things? These things are supposed to be atoms. Okay? But if you want silicon, just think of each one of these things as an atom. And here they are, all lined up in this very regular array. That's what's meant by a crystal. That's why crystals have these definite shapes, because they're arrays of atoms that are extremely regular. I mean, you look at this, and to some of you, it will remind you of driving by an orchard. Because if you look in just the right way, you get to see how it all lines up. Okay? And this regularity of the crystal has been our key to understanding what goes on inside crystals. It's this regularity of a crystal that means when a quantum wave is traveling through it, you know, a particle is traveling right down that, and a little bit's bouncing, and then a little bit's bouncing, and a little bit's bouncing. Even though it's only a little bit bouncing off each atom, the regularity of this means that there's a very large bounce by the time you've gone through a billion atoms. So you get this wave coming back, and that wave coming back bounces. And it doesn't bounce very much off each atom, but by the time it's gone through a billion atoms, it bounces a lot and it's going in the same direction. Does that wave cancel the original wave? If it does, then that wave is not allowed to exist. And these not allowed waves are the ones that give rise to the energy gaps. So that's why I brought this in here, just because it's sort of a nice, neat model I saw in the back there, and it gives me a sense. I mean, I wanted to share with you my image that I have in my mind. When I'm talking about silicon, this is what's in my mind, something very regular like that. And there's a lot of work being done now on what are called amorphous solids. And perhaps in the near future, we will have cheap solar cells, and they will not be perfect crystals like this. There'll be things that are crystals locally, but this crystal won't be lined up with that crystal. And the idea is these amorphous things are much harder to understand because the regular things, quite frankly, are very regular, and that makes for a great simplicity. When they're messy, it's harder for the physicists to understand. We have people in our physics department who you propose a structure like this. You haven't built it yet. It maybe consists of 7 different atoms in some sort of regular array. They will then build a model on the computer. And then they will have the waves go through and bounce off, and they will calculate how this material will behave. And they'll say, don't bother. And then you come up with another idea. What if I do this and this? I think it would help because if I put this thing in here, and they'll do that, and they'll put it into their computer, and they'll say, wow, that's a room temperature superconductor. Build it. More often they say, well, that didn't work, but the reason it didn't work was because these other things you put in, maybe you should try this and this. So this is the sort of computer modeling that goes on in physics now. These things are so complicated, especially if they're amorphous, very hard to guess what's going to happen. So you make educated guesses. And then you give it to the people who know how to do this in the computer, and they make an estimate as to what's going to happen if you build it. And then if it looks good, you build it and you see if it works. If it doesn't, they want to know because it means there's something wrong with their computer model. So a lot of modern technology is being developed this way, especially for high-temperature superconductors, but also for other kinds of semiconductors. We were talking about semiconductors. Remember what a semiconductor is. You have a crystal, and when I draw this crystal, position goes this way. This way is not up. It's the energy. So it's an abstraction here. I'm saying at this position, what energies are allowed? The answer is this band is allowed, and this band is allowed, and this thing is not allowed. So this is the conduction band. Now, I started talking about a diode last time. We talked about solar cells in which light comes in, knocks an electron up to the conduction band. It's conducted away. You have electricity flowing because of the light. Light produces electricity. That's a solar cell. It's also a CCD on your digital camera or your cell phone. Now, a remarkable thing happens if you do the following. And I'm going to give you more physics here than you need to know. And again, I'll tell you what it is you really need to know. You take one of these crystals, and they do something that traditionally has been called doping it. You dope it. And typically you could do that by putting in extra electrons and positive charges up here. Extra ones. I'll just draw the electrons, but there are positive charges. I'll draw the positive charges too. You put them at a higher energy in what would otherwise be an empty conduction band. So these things will conduct. The other thing you can do is take a crystal. This is called an N-type material because of the negative electrons that are in the conduction band. You can also take one of these materials, and down here in the band that normally doesn't conduct, you take away a few electrons. So this has leftover positive. Actually, you don't actually take away electrons. What you do is you put an impurity in here that gives extra spaces where electrons could fit. Sometimes these are called holes. So your conduction band, your insulation band, which used to be so full that nothing can move, now has some empty spots in it. And that allows some motion. So this thing can conduct too. Because now with a few empty seats, I say move over, and if you find a seat where you can move over. And then someone else sees your seat's empty and you can move over. So you can actually get some current flowing because there are a few of these empty seats, these holes. Now here's the great trick. First great trick of the transistor. Put these two things together. When you do that, put them together. Some of these electrons here will lose energy and come over, will come over to this side just because they're bouncing around and they're diffusing and they don't always stay put. But when they come over here, they can lose their energy, fall down here, fill up the holes. And when they do that, there are no holes left. It's not conducting anymore. But more importantly, because the electrons moved over, this side now has a negative charge. Well, wait, negative charge. They repel each other. They should go right back. Oh, but to go back, they have to gain energy. So they can't get back to this side because they'd have to gain energy because of the energy gap. Meanwhile, this side has the positive charges left over. So we actually have a charge separation taking place just by touching these two materials to each other. What I want you to know is the following, that by suitably putting together two semiconductors, you wind up getting charge to separate in the middle, and that has an effect. The key effect for this device is it's a diode. The reason is with these extra electrons over here, if you try to make electrons flow this way, they won't be able to flow because they're repelled by the electrons. Whereas if you try to make them come this way, they will flow because they'll be attracted by the positive charges. So current will flow just one way. That's one of the most important practical inventions of the 20th century. Something that lets electricity flow just one way. It used to be done with vacuum tubes. There used to be another way to do it. You'd use a lot of energy just to keep these vacuum tubes hot because they had to be kept hot. Very wasteful of energy. This doesn't require any energy. You just take these two pieces, put them together, and now you have a diode. Electricity will flow one way rather than the other. Why is that important? Well, typically, we use alternating current with the voltage going up and down, positive, negative, positive, negative. We do this so we can use transformers. Remember E&M? It's going to be on the exam. You could use transformers with AC to change the voltage. So we use AC. Edison lost that one. You wanted to use DC. You should be studying already. You should have studied the chapter in E&M, so all this sounds familiar. If it doesn't sound familiar, then you could do the rest of your class a favor by continuing to put off studying to the last minute. Most of the class will be very grateful to you if you do this. You are doing them a favor. Don't study until the last minute. Most of your classmates will thank you. Now, you put this, so you have a wire here, and here's your wire, and current's going this way, and then this way, and then this way, and then it's this way. Now you put in here this diode. Okay? And now the current goes this way, and then it goes up. Then it goes this way, and then, no. And it goes, so what happens is instead of getting this, the actual current that flows will look like this. It'll only flow one way. Now you could use this to charge a battery. A battery, you have to put all the electrons onto one side, And you don't want to take them off on the next cycle. You put a diode in there, and they'll go in, and they won't come back because no current flows the other way. So every one of your battery chargers, if you plug something into the wall to charge your computer battery or your cell phone or your iPod, it's going into a diode that lets the current flow just one way. But now we're in the beginning. This diode was the first thing. First diode was called a cat's whisker. It wasn't really understood at the time. They didn't actually use cat's whiskers. It just looked like a cat's whisker. It's mentioned in the textbook. But the next invention was called the transistor. And it was the first switch amplifier. And there are lots of transistors. This is a whole technology. It's like saying, oh, an automobile works by having a little engine here, and gasoline goes in, and it explodes, and it pushes the piston, and that's the automobile. And then people say, tell me about different octanes. What's this with a diesel? What's going on with a hybrid? How is my Ferrari really the same as my Honda Civic? You know, you get questions like this. And of course, you have here one of the major technologies of the last 100 years, which has become enormously elaborate because it's competitive, important, and valuable. Well, the same thing is true of semiconductors. It is an enormously complex field. So what I'm doing is giving you the basic ideas that are behind every semiconductor, and I'll do this with illustrative examples. The first thing you've got to know about are these diodes. Oh, by the way, once you have a diode like this, you could have current flowing from here to here. And as electrons transfer over in these holes, the more holes are made available, and more electrons can drop down if you keep on supplying them. So current will flow. But you notice there's something important going on here. The current flows in here, drops, and then flows out there. At this junction, these electrons have to lose more than an energy gap of energy. If you do this just right, they will lose that energy by emitting light. You have to do it right. You have to actually put in the right kind of atoms in there to make sure that they don't lose this energy by colliding with things, but they lose this energy by emitting light. If they do that, what do you have? You have something called a light emitting diode, also known as an LED. You have a little thing that, when you put electricity through it, will give off a light. Maybe it'll give off red light. The initial LEDs, which were used for the displays of pocket calculators back in the olden days, they're called LEDs. They were simply diodes that were specially designed so they'd give off light. They weren't designed to make current flow one way. That wasn't the interest. The interest was to make use of this drop. It's like a waterfall. But make the waterfall, the loss of energy, not be friction, not be heat, but be light emitting by putting in the right atoms. And so this huge technology, light emitting diodes, at first they were all red. Light emitting diodes are now everywhere. Every time you look at something, I don't know, we look at anything you have that has a little red light on, showing it's on, that's a light emitting diode. Light emitting diodes are used in your remote controls. You push a button and a little light emitting diode will emit some infrared light that tells the television to go on. Light emitting diodes are now being used by the city of Berkeley to replace the stoplights. Stoplights used to be bulbs, tungsten bulbs, with a red filter in front of them. And this light would come out. It would be, yellow light with a little bit of red. The red filter would cut out all of that so that some of the red light came out. Waste a lot of energy, and there it would be, and you would look at the red light when this light was turned on. Now they're replacing all these with basically a large number of light-emitting diodes that emit only red light. And these are much more efficient. And they just turn on the light-emitting diodes. And if you look at street lamps in Berkeley, most of the red lights have been replaced. The green lights haven't yet. That's because green light-emitting diodes are something new, and they're still more expensive. Most expensive of all are the white light-emitting diodes. those are actually light-emitting diodes that actually emit light in the ultraviolet. And then they have a phosphor that absorbs that and emits it in the visible. But they're called white light-emitting diodes. And in the next 10 years, you're going to see a transformation in the technology of flashlights. I should have brought one in today. Didn't think of it. I just bought a flashlight, a little flashlight. It's about this big. Okay, and it's as bright as a big flashlight that you normally carry by the police. This thing is rated for use by the police. This tiny little thing. It uses light-emitting diodes. Because they're so efficient. The batteries will last for hours, and yet it'll be much brighter than an ordinary flashlight. It's replacing the tungsten bulb, which puts most of its energy into the infrared, very wasteful. This puts a large fraction of its energy into the visible and makes a great flashlight. I bought this specifically because I want to be able to see animals in the middle of the night in Africa. If a lion is stalking you, very handy to have this because it's almost like radar. You turn this thing on and shine it into the darkness. And you see these two little lights light up. Those are the eyes of the lion. Because they're retroreflectors. Remember that? Midterm. They're retroreflectors. It also gives rise to red eye. You turn on this little light, and not enough comes back. You can't see the mane of the lion, but you see the eyes light up. I have never seen lion eyes light up in the darkness, but I have seen bear eyes light up. One that had stolen my food up in the tree. I shine the light up, and you see these two little things light up, because the eyes are retroreflectors. So I have this tiny little flashlight, saved me from the lions, going in May, right after the final exam. Never been there. So these are light-emitting diodes, an enormously important technology. They are now using light-emitting diodes on these huge display TV screens. You go to Memorial Stadium and watch the football game, and you say, wow! Now what really happened? You look up at the screen, and they have the instant replay. Out in the daylight, they have this big screen with all the colors. How do they do that? Little light-emitting diodes. They have red, green, and blue. And instead of projecting it, instead of using some projector light, these things just emit the light. And the little signal comes in and says, this little pixel right here is supposed to be green. And a moment later, it'll be red. So they'll first turn on the green one, then they'll turn on the red one. And they can create a picture out of this using light-emitting diodes. And you can look at one of these things up close if you ever get a chance. It's sort of hard to do at Memorial Stadium. I don't like you climbing up there. But there are other places you'll see it. You go to New York City, go down to Times Square, you'll find Times Square used to be covered with light bulbs. Now it's covered with light-emitting diodes everywhere. Big pictures that change. They're basically big TV screens. Do we have home TVs using light-emitting diodes yet? No, we don't. A little bit too expensive, but we will. Sean. Sean just happens to have a little flashlight with a light-emitting diode on it. It's part of his cell phone. How can you get a cell phone without a light-emitting diode in there? Notice how white it is. What's all that? Oh, that's the class. Look at that. I can take pictures of you. Anyway, this is supposedly to give extra red eye, so that when you photograph someone, their eyes light up. Use it as, no. That's pretty bright for just throw on. Okay, high tech. Good. So that's the LED. Now, can you do better? Question?
So that shines light because the current goes through a semiconductor, causes the electrons to jump the gap, and then the energy releases light.
Okay, the question was, Sean's light works because light goes through the semiconductor and jumps down the energy gap and causes the electrons to emit the light. Very well put. The answer is yes. There's one of these questions where the most effort is spent restating the question. So our friends in Holland, hello, friend in Holland, thank you for writing me and telling me that you're listening to me every day when you work out on the podcasts. Best greetings from the whole class. Class, say hello. Okay. That's the most distant response I've gotten so far is from Holland. The idea of someone working out while listening to physics, I just love it. Another person on the East Coast says he does it on his static bicycle. And what do you do on a static bicycle? I used to go play racquetball to entertain the people who were on the static bicycles. They always pretended they weren't watching us. So every time, the point was over, they'd be looking down again. But I was sure they were watching us. But better than that, listen to physics. Okay. Now, better. Suppose you could arrange this whole thing so a large number of things all fell down together so that you put the right chemicals in here, and this is, again, an issue of impurities, so that they wouldn't fall down instantly, but would hold up for a while. In other words, what happens is the electron falls, but the energy gets transferred to an impurity atom that's in an excited state. You can do that. Okay, so let me just say that again. The electron loses its energy, but instead of emitting light, what it does is it transfers its energy to an impurity atom that doesn't lose the energy right away. It stays there in an excited state. And you do this to a lot of these things. So you have a lot of atoms in the excited state. And then one of them gets around to emitting a photon, and that stimulates the others to losing a photon, and what you have then is a diode laser. That's what a diode laser is. These are diode lasers. They have a diode with impurities that hold the energy long enough so that it's emitted when it's stimulated to emit it by another light, and we get these wonderful diode lasers that we're seeing everywhere. Most lasers you see these days are diode lasers. You see them in supermarkets. You see them in physics lectures. You'll see them in many, many other places. They're being used for communications. Okay, so these are the diode story. But now, let's take it one step further. And that is to create the switch. So the switch is the next key invention based on semiconductors. I described there are many kinds of switches using semiconductors. The thing I'm going to describe is something called a MOSFET. There's some optional material for this in the textbook. I will tell you what I want you to know about this kind of a switch. But it basically consists, most of these switches consist of 3 semiconductors. Okay, and this will be an N material, this will be a P material, this will be an N material. You don't have to know that. What I want you to know is that these things are designed. This is like a diode. So current cannot flow. That's in the typical NPN junction. In a MOSFET, it's a little bit different. There you have conduction. What they do is they have a conduction band here that has electrons in it. They have a conduction band here that has no electrons, and they'll have one here that does have electrons. And because there are no electrons here, current can't flow. Now, you might have a huge voltage here, and the current would love to flow, and it builds up electrons, but that repels the rest. So it just can't flow if there are no electrons to flow. It's like having an insulator in the middle of 2 conductors. So you have this big current that's just wanting to flow. It's like a dam. But there's no place it can't flow in here. You have to have electrons to flow. You think they could push their way in here, but if they push their way in, they repel the other electrons because there's really no place for them to go except very high energy states. In fact, this probably, well, let me not get into too much detail. I was going to throw the energy state up. But now what you can do is the following. This is the way it works. You put a control electrode here. With this control electrode, you can change the voltage here by a little bit, and that will bring electrons into this state. They can't be there by pushing them in, but you can control them. It's like opening a valve in a dam. Water can't go over the dam, but with a little bit of control, you can let it through. It doesn't take much energy to open the gates. And when you open the gates, you get this enormous flood coming through. So what you can do is with a little bit of voltage, you create conductors in here. Once you've done that, this current can really start flowing. The key concept here, I like to call the valve or the switch. You know, if you are running a faucet, you can go and you can, relatively easy to turn the knob, at least with some knobs, but it should be easy. You turn the knob, and then the water comes gushing out with a huge amount of energy. And then you turn the knob, and it stops. You are controlling a large amount of energy. Now, what this is key is this is what an amplifier does. I want you to know the concept of an amplifier. An example would be your iPod, your music player, your actually TVs, radios, they all have these things in them. What they do is they take a very small signal. The signal might come from a radio wave, really tiny signal. You can't hear it. Your ears aren't sensitive enough. It's not, your ears don't hear electromagnetism anyway. But if you were to take this and make it go through a wire, which you can do, that's called the antenna, then you hook that wire up to a speaker, it's such a weak signal, it won't move the paper on the speaker very much. It won't make audible sounds. It's too weak a signal. What you want to do is to have a very strong version of that signal that identically mimics the weak signal. So what you need is a faucet. You want that weak signal to basically turn the faucet on and off and have the huge flow of energy be controlled by this weak signal. So you turn it on, turn it off, controlling a lot of energy. It's like pushing the gas on your automobile. You just push a little bit and the car goes zooming forward, and you push a little bit on the brakes and you stop. You're controlling a large amount of energy. In Britain, they call the things that do this, they call them valves. In the United States, they used to be called, in the olden days, your parents will remember this, maybe, if they're old enough, they used to call them tubes. An old TV or radio had these tubes in them, vacuum tubes they were called. They would do this thing. The British called them valves. Now we make them using semiconductors. And so this basic idea is the most common type of valve. Where does this current come from? Well, that current comes from the battery. So you have a battery that supplies all of the energy, and then you have a very weak signal that controls the flow. The very weak signal could be a weak signal that's coming off out of the computer memory, if it's an iPod. It could be a weak signal that's coming off the spinning disk, a magnetic disk, if it's an old-fashioned iPod. It could be the weak signal that's coming from the antenna, if what you're listening to is a radio program. That weak signal controls a big signal. Now you have an identical copy, because this thing is going, on, off, on, off. And this thing is going on, off, on, off. So it's just controlling it, like controlling a valve or faucet. That's what an amplifier is. So everything that uses an amplifier, those of you who are stereo buffs, stereo basically means two. You're hearing with both ears. The old term used to be high fidelity. Then when I was a kid, people started going stereo. And the whole idea of stereo was it really sounds a lot better because your two ears do work independently, and they help you separate out sounds if the signals are a little bit different from each other. So they took high fidelity and changed it into two high fidelities. That became called stereo. Now everything is stereo because the quality, the experience of listening to stereo is so much better. But basically, stereo amplifiers are things that take the small signal that come from your compact disc, from the laser hitting something, it's a small signal, make it strong, and use it to control a very strong signal, usually a DC signal, because they want DC. The DC signal, of course, is made from the AC in your wall by using a diode. Use it to control this DC, which then makes the speakers vibrate, which push on the air, that pushes on the drum, that go into your inner ear, that go into your brain, and I've never figured out where they go from there, but it's somewhere. So that's what an amplifier is. Now, the ultimate kind of amplifier is simply the on-off switch. It not very complicated. You just put enough voltage on this that things flow, or so that they don't. And this, with the on-off switch, is the key to all computers, all modern computers. They're all based on switches. You look at an elementary computer book for introductory computers, and they will talk to you about using switches to be able to add numbers. If you have a switch, it can be in two states. It can be flowing or not flowing. That could mathematically be represented by the numbers 0 for not flowing and 1 if it's flowing. If you want to put the number 1 down, you can do it in binary by writing it as a 1. The number 2 is written this way. The number 3 is written this way. The number 4 is written this way. The number 5 is written this way. The number 6 is written this way. The number 7 is written this way. So this is a code. It's called binary. If you want to know what it is, if you want to know what number this is, you say, well, this is the one digit, so that's 1 plus 2 plus 4. That adds up to 7. Okay, you don't have to know that. What you do need to know is you can represent numbers with switches. So you can put any number you want into your computer if you have enough switches to be able to put it in there. They're on, off, 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 on, off, 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 on. That's the number. You can get 2 of these numbers. Now, what do you do if you want to add them? It can be done with switches. You have one switch control another switch. If this is a 1, then you turn if this number is a 1 and this number is a 1, only if they're both 1s do you turn this switch on. That's the basic logic element. The fact that you can do addition with this is amazing. All you need are switches and you can do addition. I'm not asking you to know how these switches do addition, but they basically work on this process that if the 2 switches are right, they will turn on another switch, and if they're not right, they won't. And doing this, you can do addition. Once you've done addition, it turns out you can do multiplication too. You know, multiplication is basically memorizing a list of rules and then doing additions. What about other things? Well, every computation that can be done, as far as we know, can be done by using these simple switches. There are some things we haven't quite figured out yet. We don't know whether there are limitations. We don't know whether there is something that can be done without switches that we haven't found yet. You know, maybe something in the mind, a certain type of creativity that's impossible to do with switches. We haven't found the limit yet, but that's only because there's so few things we can really do. Certainly working with numbers is absolutely easy. Working with pictures is really easy. Recognizing a face, well, no, we haven't done that yet. Translating a language, we done that yet? It's amazing, but there was a breakthrough, a major breakthrough, I think it was about a year ago, in translating languages that so astonished me that I realized for the first time that translating languages is imminent. This was done by this great research organization known as Google. And they entered contests to translate. Everybody, until this came out, I believe, I'm not an expert in this, but everybody that I knew who was working on this was basically, look, the following is absolutely obvious. If you're going to translate a language from, let's say, I don't know, Arabic to English, okay, the first thing you do is you take that Arabic, and the first step, this is obvious, is you have to understand what's said. Once you've understood what's said, you then take the Arabic and put that, and you then take that understanding and put that in English. So this is the obvious way. And it turns out it's wrong. I had assumed it. I never explicitly said it. I never stated this because the assumptions that are the most pernicious are the ones we don't know we're making. That's true in politics, religion, and physics. You don't know you're making it, and you just assume it's true because isn't it obvious? It used to be that way in the Middle Ages when, through much of Europe, Christianity was considered obvious. Now we were doing it with translation. So what is the key? Why don't you mean you don't have to understand it to translate it? Right. That's the great breakthrough. This is a scientific breakthrough that took place in the last year, and it's going to be absolutely revolutionary. Google's simple idea is they have this huge database. They have all these millions of documents. Pick all the documents that have been translated. This has been translated by a person. This has been translated by a person. Okay, now, they never really disclosed what they did, but this is my guessing as to what they did. Now you have a sentence in Arabic you have to translate. So you look through all your other documents. They're really good at this. Find that phrase. Those of you who have been cheating on homework have learned it's not that hard to do, to go through lots of documents and find sentences and phrases that are the same as other students' homeworks, or those of you who've been accused only of plagiarism or caught only plagiarism for copying whole sentences out of newspaper articles without putting quotes around it. That's called plagiarism. It's easy to do on the computer. So here's what Google does. You have this document, you don't know what it means. You look through your millions of documents, you find something where that part of the sentence was translated previously by a human. you'll find it 18 times. And so here you have a list of the 18 possible translations, some of which are the same. How do you pick them? Do you pick the most common one? No, you may be wrong. What you do then is you look at the rest of the paragraph, and you find other things. And you see, does this paragraph relate more to this translation, or this one, or this one, or this one, or this one? You make the best guess. Oh, this one seems to be doing the same subject because it has a lot of the same nouns and verbs as this particular one. Therefore, I'll pick that sentence fragment and translate it in this way. So they do that. It doesn't require any thought. You don't have to know the meaning. And they have won every translation contest. They entered hands down in getting accurate translations. So this is imminent. You know, they're going to, I mean, this is a technology that they have just demonstrated, and computer translation, I believe, is around the corner. Would not have believed that a year ago. Okay. So there are these things, however. By the way, computers are also very good at making beautiful music. It doesn't touch my soul in quite the way, but it's quite pretty to listen to. So we don't know what the limitations of computers are yet. But people who say they're unlimited have no basis for saying that either. Is there a difference between humans and computers? I don't know. I think there is. It may be simply quantum mechanics, because we don't have quantum mechanical computers yet. We'll be getting to that shortly, talking about quantum computing, which so far isn't very successful, but it's a lot of fun in research. So that's what switches are. An amplifier. The difference between an amplifier and a switch is with an amplifier, you want the signal to be medium loud as well as on and off. You want my voice to become my voice. That's an amplifier. You want my voice to become my voice. By the way, a lot of amplifiers have what's called gain control. If the signal is weak, they make more amplification. That way, when I whisper, you can still hear me if it has automatic gain control. It's just a little electronic circuit that sees how big is the oscillation. And if it's not very big, it makes it bigger so you can hear the whispering. Those of us who love great music hate this, because some musicians will do something. Tchaikovsky's Sixth Symphony. You know, it's part of what you do when you're doing music. And if the automatic gain control turns up the really quiet stuff, which is lulling you to sleep, you know, Haydn's Surprise Symphony, you know, has this big note. Beethoven used it all the time. It's one of these tricks. Many of us find certain kind of music, although it's really nice and fun, and you enjoy it and you get into it, you know, after half an hour you're kind of bored with it because it doesn't have those surprises. Some of us like that kind of music with surprises. And it amazes me how I can be surprised even when I've heard it the 59th time. I just enjoy that surprise coming. Last thing I want to touch here is tunneling. Tunneling is something that is an essence of quantum mechanics. You will hear a lot about it. There's a lot of misunderstanding about what tunneling is. Tunneling is sometimes described as the fact that in quantum mechanics you're allowed to violate energy conservation, as long as you do it quickly. What it means is I could walk through that wall as long as I had this demo of tunneling. I wonder I didn't bring in my tunnel demo thing. I need the right piece of chalk. Where is it? Oh, this looks about right. Okay. Okay, so here's the tunneling demo. Okay? We'll go over here. According to ordinary mechanics, this cannot go inside my hand because it would have to stretch the atoms apart and make the hand, and that takes too much energy. But in quantum mechanics, it's just a wave. And a certain fraction of that wave actually gets inside. It's a very low amplitude, but it is a fraction of the wave that gets inside. And because of that, there is some probability that this thing can just go through. And normally, if we're lucky, that probability will happen right now. Let me do that over here. We go. Ready? I'm going to see if I can take advantage of that probability and make it go right through. One, this hurts sometimes. Ready? Because I'm depending on quantum mechanics. This doesn't work in ordinary mechanics. There. Okay. So it worked that time. You were lucky. I had a student of mine one time come up to me after class and said, Professor Muller, I can show you a better way to do that. I said, oh, he was a professional magician, a student. It wasn't this class, but a student in a physics class. He was also a professional magician. And he taught me a way of doing it, which is what I just did for you, which is a little bit better than the way I used to do it. You know, there's another way to do this, which is, I'll take something like this, you know, and then take it and go, boom, it goes right through. So there are other ways, but he showed me that way. He then went on to do the definitive test of astrology, which got published in Nature magazine. I was his scientific advisor. He got his PhD in physics, went on to found the Society for Amateur Scientists, and he got a MacArthur Award. John Carlson. My relationship with him started with a tunneling demo. Okay, so tunneling takes place because even though it would take too much energy to actually put this thing in here, and it would have to push the atoms apart, quantum mechanically the thing's really a wave. And so here's the wave, and a little bit of the wave extends in, and waves extend into matter. They're very weak, but they do extend into matter. And so there's some of the wave over on this side, and because there's some of the wave over on this side, there is some probability that you will find the particle over there. So let's talk about this interpretation of quantum mechanics. When you make a measurement, we're getting into Schrodinger's cat too, a little bit of free will, nuclear decay. So this is the quantum physics for philosophy majors. But it's also the sort of thing that you will come across. Oh, by the way, there's do I have my reference here? Let's see if I have it. The stuff we're about to be talking about, like in the uncertainty principle, my daughter studied in a philosophy course at Columbia University. Not a physics course, a philosophy course. It was a course, and the course was taught by a man named David Albert. Who, like me, is a physicist. And they used this book that he wrote called Quantum Mechanics and Experience. And she started talking to me, and I realized that this daughter of mine, who had not taken any college physics, understood quantum mechanics better than almost any physics major I knew by taking a course in the philosophy department. And the course was designed for people who are not expert with math, but they can't be too afraid of it either, because it doesn't go into the kind of math that's really scary. The math is very simple. It's just abstract. If you can, any philosophy major, any linguistics major knows how to handle very abstract thoughts, because those subjects get as abstract as anything in math. In math, you have to sometimes learn how to do computations, and a lot of students don't like that. This uses very simple math, but it's an abstract kind of math, which I'll be talking about a little bit today. What I want to say is those of you who really want to know more about this kind of quantum mechanics, quantum physics, I really recommend Albert's book. It's not an easy book, but it's not you know enough math to do it already, everybody here. Now, he will teach you things, and you'll have to say, oh, so a particle is in a quantum mechanical state. You'll have to think about, you may be confused about that. You'll have some background from this class. And then he'll talk about superposition of states, as I am about to now. We're only spending half an hour on this. You really want to know this stuff, and some of you really want to know this stuff, I highly recommend Albert's book. It's the place to go to get well beyond what the typical physics major and many graduate students really understand about quantum mechanics. So it's a great book taught at the level where it doesn't assume you know anything beforehand. Last time I looked at this, I looked it up and you can get it for $12 on Amazon, used. Of course, I buy all my books on Amazon used these days. They're so much cheaper. And often the used books are absolutely they say condition like new. And when they come, they are. Well, they're not like new. They look like they would look after I had them for a day. So they're, for me, effectively new. And I buy all my books on Amazon used these days. You get it for 1/3, 1/4, 1/10 the price. And this thing is available, was available there for $12. Of course, that's before 11 a.m. when you guys, some of you I see working on your computers already, ordering the book. There may not be any left in a few minutes. Okay. But no, you don't have to know that stuff. But I'm going to tell you today some of the things that are in that. And one of them is the tunneling. Now, this wave function, what is a wave function? I said every particle is a wave. Here's an electron. Okay, I'm representing it by a wave, but in fact, it's not a wave. It's a particle wave. I draw a wave. Actually, I draw a squiggle of chalk. But it represents a wave, but it's also supposed to represent a particle wave. And what does that mean? This is one electron. We can make it so this thing is just one electron. But where is the electron? Actually, the position of the electron is not well defined. It is not here. It is not here. It is over this range. Get ready for the key word. It is uncertain. This is the meaning of the uncertainty principle. It sounds really, sophisticated. Oh, quantum mechanics is based on the uncertainty principle. Baloney. It's not based on the uncertainty principle. Quantum mechanics is based on the principle that particles and waves are all wave particles. Once you say an electron is a wave particle, then its position is uncertain. The uncertainty principle is a result of quantum physics. It's a result. Once I told you that particles were waves, or particle waves, and you said, okay, I'll accept that. At that point, you knew the uncertainty principle. You know the position is no longer here, 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 or here, but it is spread out. Now, some people mistakenly interpret this. This is common among elementary physics majors and chemistry majors and people taking those courses to mistakenly think that this is a measure of the uncertainty of our knowledge. That, oh, the electron is really there somewhere. We just don't know where. This represents the probability. That is the most common misunderstanding. Those of you who are physics majors in here, and there are several, you may have learned quantum mechanics and think, what's Muller saying? He's telling me the opposite of what my professor said. Not true. You misunderstood when your professor told you this. What's really going on is the electron is not a particle. It's not a particle hiding in a wave. It's a wave particle, and we can represent it by this wave. Why do we say it has a particle-like property? Because if this wave hits a surface and energy is absorbed, the energy will be absorbed suddenly, not spread out over time. This is what we call a measurement. This could be a light wave. This light wave is coming in. A light wave is also a photon. It's not a wave, it's a particle wave. This thing is coming in, hitting a surface, and at some point it's going to knock out the electron. And when it knocks out the electron will get all of the energy. That's the photoelectric effect. That electron will pop out, and we'll use it for a solar cell or a CCD camera or a Xerox machine. This thing comes in. At some point, all the energy is absorbed. When that particle comes out, can't we say that's where the particle wave was? That's where the photon was? A lot of people will say that. They say this thing comes in, and when it starts to come in and hit the surface, well, nothing happens for a while. And in quantum mechanics, the following rule is true. If you want to know when that electron will come out, what you do is you look at this thing, and you say, here's where it's most probable. Here's where it's least. This is also low probability. And here it's 0. So this is what's sometimes called the Born interpretation of the wave function. You don't have to know that. But you may have heard it for those of you who have been reading about quantum mechanics. And this is a probabilistic interpretation of quantum mechanics. What it really is simply saying that when this wave packet is absorbed, this tells us the probability of when that electron will come out. It doesn't tell us where the photon is. Now, a lot of people will think, they'll think just to make it easier to understand this, they're going to say, okay, I'm going to just forget this. I'm just going to think of it as that's where the photon really is. And they won't get them into trouble. Most physics majors can think that way right up to graduate school, and they can do computations, and it never bothers them until they get to these strange phenomena such as quantum teleportation and quantum computing and other things that have been in the news recently, the Einstein-Podolsky-Rosen paradox, these things that are really driving people crazy because these things are a key. They all depend on the true interpretation of quantum mechanics. And the true interpretation of quantum mechanics is so disturbing that even Einstein never was comfortable with it. He thought it violated the theory of relativity. And in fact, I'll convince you that it does. So this is a problem. It turns out to violate the theory of relativity, but not in any way that can be detectable. That sounds like nonsense to you. Yeah, well, we're getting into some pretty deep quantum mechanics at this point. So what do I want you to know from all this? I want you to know that an electron is really a particle wave. That the particle wave may be very intense in certain regions and very weak in other regions. This represents some sort of a probability as to when it's going to cause something to happen. But it doesn't really represent where the particle is. It's more of a probability of an event occurring than it is a description of something hidden. Sometimes there's a term called the hidden variable. The hidden variable is the thing that someday we will find out that this is not, the particles are not really particle waves, they're really particles. And the thing we call the wave function is really simply a description of our uncertainty. There is a hidden thing in here, we just don't know what it is. That's the real position. That's the hidden variable. This is all wrong. If you think through the hidden variable, you can wind up making predictions. And if you make these predictions that are testable, they have been tested, they turn out to be wrong. Hidden variable theory is wrong. Every measurement that has been made is to ask whether true quantum mechanics or hidden variable theory is right. It's turned out to be the hidden variable theory was wrong. So far. Maybe someone will come up with a new hidden variable theory, but the easy ones are easy to rule out. Getting very abstract here. Do future presidents need to know this? No, I confess. We've gotten beyond the realm of the things you need to know. Some of you in this class actually want to know some things you don't need to know. Or at least you don't want to be intimidated when some physicist comes in the room and starts talking about quantum computers. And so to that extent, you need to know this stuff. But we're getting here to a level of abstraction. In fact, most of this stuff, there's no way I would put any of it on the exams other than a few statements like hidden variable theories experimentally don't work. Hidden variable theories are theories that deny that we really have particle waves. They say it's really just a hidden particle. And those have been ruled out by experiments that I'm not going to have a lot of time to go into, although I certainly can. So let me talk more about this particle wave. Just let me confuse you, especially those of you who have actually studied quantum mechanics and therefore probably have a misimpression as to what's really going on. So here's some more confusing things. Let's take an electron in an atom. Now the electron can be in this orbit if it has the right number of waves. This is one of the allowed orbits, okay? And the electron can be in this orbit. Okay, these are the two allowed orbits. Can't be in between, right? Could the electron be in both orbits at the same time? Those of you who have studied quantum mechanics probably have an opinion on this. After all, we get light emitted when it jumps from one orbit to another, right? Could it be here and here at the same time? They have different energies. How could it be in the same, how could it be in both of them at the same time? Okay, I want you to know this. An electron can be in two orbits at the same time. It can, yes. Can it be in three orbits at the same time? I want you to know this. Yes. What's the limit to the number of orbits it can be at the same time? None. What? Yeah. Huh? Uh-huh. How can that be? That's existence. Wait a minute, suppose I measure it. Suppose I look to see if it's in this orbit. Suppose I destroy this orbit and see if it was there. Well, if that happens, if it's in many orbits and you start looking, it will appear in one orbit. You will force it to be in that one orbit. You will destroy the wave function, the particle wave, and you will change it. The process of measurement changes the wave function. If you want to study each one of these orbits, if you study this and find it's not there, then it's not there anymore. It's in all the other orbits. You have changed the wave function. You cannot measure anything without changing it. This has turned out to be very important for people who have worried about Star Trek and whether or not, when they are beamed down, they really can be. I mean, look at you. Right now, you have electrons in your orbits. Is each one in one orbit? No, it's in a mixture of orbits. Each one of us is like this. If you want to beam me down, then how are you going to beam me down? You got to know which orbit it's in, but it's in multiple orbits. And if you try to measure it, you'll destroy it. So you have to measure it in order to find out what orbit it's in, but that will change it. You measure every atom in me, and you have changed me. You've probably killed me. And now you're going to beam me down, beam down a dead body. Okay, so this is a serious problem. Okay? I don't know how many of you caught the logical flaw in the example I just gave. I didn't catch it until, for many years, I was a real fan of Star Trek, but said, I got to have, it doesn't work. And then a couple papers came out and pointed out the logic was wrong. You recognize the analogy between what I just said in how you transport somebody and the argument that I gave for why I thought computer translation wasn't around the corner? Remember, for computer translation, I said, well, first you have to understand it, and then you put it in the second language. And Google says, no, you don't have to understand it. Just put it in the other language. I had an assumption I was making that was so implicit I didn't know I was making it. And these are the really great leaps in invention in my mind when someone realizes, oh, wait a minute, wait, let's try this without, maybe they stumble upon it. They discover that the Google search engine works without understanding anything. So why not translation without understanding anything? Okay, so quantum teleportation is the following. And this came as a shock to me. You do not have to measure something completely and then reconstruct it. You can actually recreate a quantum state at a different location without measuring it. Now, it turns out that it's a little bit more complicated than that. And I don't know how much time we'll get to go into this. But what you do is you have to take an atom, one atom for every one in my body, okay? You got to do this. This is how you're going to do it on the quantum teleportation. You've got to take one atom for everyone in my body, but they're not me yet. Then what you do is you separate these atoms into what are called entangled states. That's like this state and this state may have the electrons both up, one down, one up, and both down. But they're in the state together. I don't expect you to really feel comfortable with this. I'm not going to put this on the exam. Okay, I want you to know what quantum teleportation is. You then have this atom here, you take this atom here, you put this atom down on the surface of the planet, this atom is up here, you have transported what are called entangled states. Now you want to beam me down. At this point, I go up to this entangled state, and I am measured together with that entangled state, thereby destroying me. But because I interfere with the entangled state, Scotty now sends down a couple of bits that tell them how to rotate these entangled states, and they do that, and now there's Professor Muller down on the surface of the planet. And he'll be quantum mechanically identical to the one up here who was just destroyed. If you don't follow that, it means you're being honest with yourself. Okay? This is not an easy thing to follow, but I just wanted to show you the thoughts that are going through in people still trying to understand quantum mechanics. Question? Does this mean I'm killed and reborn? Well, now we're getting beyond physics. I think there's a real question here. Is that Professor Muller down on the planet me? Or is he just a new being with all of my memories? And then you get to the question of, what's the difference? And now we are way beyond physics. Okay. Let's put it this way. I wouldn't let him do it to me. Well, let me talk about this measurement. Measurement changes the wave function. Now I'm going to talk about something I do want you to know about. It's called Schrodinger's cat. And this is the fact that you can be in two states at the same time. By the way, imagine the following. Suppose you have a flashlight, and the flashlight emits two frequencies. And the two frequencies are slightly different. They will have beats, right? Beats, like sound. They'll have beats as they come in and out. They really consist of two frequencies that alternately reinforce, and then they come over here and they cancel because they're slightly different. That gives beats. Send a light beam like this. Suppose it's a very weak light beam. It's so weak that it only has enough energy to absorb one photon. When this beam hits, which color will it be? Will it be this one or this one? If they're the same amplitude, 50% chance of being either one. So even light beams have the same issue. They could be the superposition of two states at the same time. The atom could be two superpositions of two states at the same time. Until you measure it, you don't know which it was. So Schrodinger said, Professor Born, that's nonsense. Let me demonstrate it. And he demonstrated it with a thought idea. He said, I have a box here. In the box, I'm going to put a cat. Those of you who are squeamish about cats, please forgive me. This is his example, not mine. These days, we would use something that most people detest called a hyena. But I actually like hyenas. I'll use the cat. So we have a cat in here, and we have a radioactive atom. Now, a radioactive atom, it turns out, if you look at it quantum mechanically, you know, the radioactive atom will suddenly choose to decay. Well, I'm being a little bit anthropomorphic here, aren't I? Choose to decay. Well, the radioactive atom, according to quantum mechanics, is a superposition of two states. It's a superposition of the undecayed state and the decayed state at the same time. This is how we think about it in quantum mechanics. If you actually measure the presence of an electron that came out from radiation, then you have determined it's in the decayed state. But unless you look at the atom and find it's still there, that's a measurement, or you look at the electron that's come out, that's a measurement, you are in the superposition of states. Well, Schrodinger just couldn't take that. He said, okay, fine, you can feel that way about atoms. We can't see atoms. Let me put one in a box with a cat. This radioactive atom, when it decays, is going to shoot and kill the cat. Sorry about that. Now we have a box. You're not going to look inside. It's just this radioactive atom, which is, until you look at it, a superposition of two states. Right? One of them is the decay in which the cat is dead. The other is the not decay in which the cat is alive. So inside this box is a superposition of two states consisting of a non-decayed atom and a live cat, and a decayed atom and a dead cat. Okay? So what you've said about quantum mechanics is clearly ridiculous. You can't have a box with both a live cat and a dead cat in it. So what's the answer to this? I can give you the answer in 3 words. Oh. Maybe the cat has the power to make measurements. What is a measurement, after all? A measurement is something I go and I look. Am I the only one allowed to make measurements? No, you're allowed to make measurements too, right? What about cats? Do you have to have a soul to make a measurement? Right, does the soul really exist? That's not a physics concept. What does this mean to make a measurement? The fact is, in physics, we don't know what it means. The theory of measurement isn't really understood. But what of the great interest in quantum computing is that it forces us to confront what we do know and don't know about the theory of measurement. Because the way quantum computing works, the whole key to quantum computing, is basically Schrodinger's cat. So here's what I want you to know. I want you to know Schrodinger's cat simply says physical systems can be in many states at the same time. And if you get to the ridiculous example that Schrodinger loved to tease people with, he said, yeah, that means a cat can be alive and dead at the same time. By extension of this physics that you are coming up with. I mean, the physics seems to work everywhere we do an experiment with atoms, with molecules, with light. This superposition principle holds up. But when you think, how could it possibly hold up for cats? You know, well, Okay? But this is what quantum computing is based on. Now, here's the way quantum computing works. You can have these atoms, and each atom can be, you know, on or off, right? You can have it up or down. You can have the switch on or off. That's how all computing is done. Well, wait a minute. How about having it on and off at the same time? Can you do that? Well, in quantum mechanics, you can. Just like you can be in several states at the same time. You have one state being on, the other state off. This is a 0, this is a 1. You can be in both states at the same time. Why would you ever do that? Well, if you're in many states at the same time, you can have a relatively small computer, and you could put many different problems into it at the same time. For example, this 37-digit number. You can say, is it divisible by 2? That's a problem. You could work that out on an ordinary computer. Is it divisible by 3? Is it divisible by 5, by 7, by 11, by 13, by 17, by 19, by 23? Is it divisible by the prime numbers? Well, God, you have a trillion calculations to do, more than a trillion. But in a quantum computer, you put them all into the same computer at the same time. Because what you do is you represent each one by a superposition of these states, and then you can compute on them simultaneously. If you measure it, you destroy it, so you can't measure it. What you need to do is to have the computer spit out an answer. If it finds that this is not divisible by any of these numbers, then you know it's a prime. More importantly, for cryptography these days, is to find the number that divides it. Turns out that's something, I could talk about that at length too, but much of cryptography these days is based on numbers that if you could factor them, you could break the code. Factor them meaning find a number that divides it. If you could do this on a quantum computing, I have 10 zillion computations all going on at the same time in a relatively small computer. So some quantum computing has been done now based on a small number of atoms, like adding 1 and 1. That's been done on a quantum computing. Can you go from that to making a quantum computer that instead of having 2 elements or 5 elements, has 10,000 elements? That's all you need. Maybe even 1,000 would do. You don't need that many different elements. If you could do these computations simultaneously, this would totally transform what we could do. The calculations would not be 1 billion times faster. They'd be 1 zillion times faster. So this is the idea of quantum computing, and it takes advantage or uses the fact that an atom can be in several states at the same time, and these two states can be transformed together, which means you can do computations on many different numbers all simultaneously. And it has been done in very simple cases, but is it going to hold up? Or are we going to discover that this understanding of quantum mechanics and our theory of measurement is really as crazy as Schrodinger thought it was with his cat? And we're getting down really to questions here of free will. Okay? And I like to point out that free will, I've talked about this earlier, but let's get back to it now, because I talk about, do I have free will? I still remember vividly, 1978, I was going to name my daughter. My wife and I talked about it. We talked about what we knew about history, what we knew about people, all these people you don't like, all these people you like. They're the famous movie stars. You don't want to name them after them because that, and so you try to come up with something that's very personal. We decided to name our daughter Elizabeth in 1978. 1988, the daughter's 10 years old. We now call her Betsy because we hope that someday she'll change her name back to Elizabeth. And we love the name Elizabeth. And I'm curious. I'm saying, what were other people being named? Look at Northern California. What is the most popular girl's name in 1978? And I look it up, and it is Elizabeth. I begin to wonder whether I really do have free will. You start thinking, what is free will? Does free will mean you make decisions without influence? The fact that there was this wonderful program about Queen Elizabeth on, where I have to ignore that? Does free will mean that people give me suggestions, I ignore them all? Or that I am affected by them and choose freely? Choose freely? The people who are more effective in persuading me to vote for this candidate than another candidate, is that a free choice? Well, I argue with them, but I'm using arguments I've heard from others. I make up a new argument, but did I really make that up? Or am I using what I learned in Physics for Future Presidents? Am I really free? What does it mean to be free? Does it really mean, philosophers can't come up with a good definition of what free will means. Free will, if it means totally unaffected by any outside force, I almost lose interest in it. But that's the best definition I can come up with. And we do have examples of free will, because we can take 2 potassium-40 atoms, and we can make sure they are absolutely identical. How do we know they're identical? Because they're waves. And if they're waves, we can cancel them and reinforce them. And you could use cancellation and reinforcement to see if they're really identical. Because waves that are different will have beats. If there are no beats, these things are identical. We can prepare 2 potassium nuclei, potassium-40 nuclei, put them there, and we can know they're absolutely identical. Then we went around. for them to decay at the identical time, but they don't. They choose different times to decay, even though they're identical. This is a principle in quantum mechanics. The decay is random. Does that mean the potassium-40 atom has free will? Well, according to the best definition I have been able to come up with in philosophy, in thought, you come up with the best definition, the one thing I can really show you has free will are radioactive atoms. Do we have free will? It's really hard to define. Are we driven by quantum mechanics to have free will? Because if atoms have free will, if the electron position is uncertain, and so it has some free will, maybe that's the origin of our real free will. But if that real free will simply means our choices are random and not affected by other people, then is that such a thing to be proud of? We go on to relativity on Tuesday.